Hello, this is part A of the Chapter 9 lesson. Chapter 9 is titled Multivariable Methods. And as the title suggests, we're going to be dealing with situations where we have more than two variables involved. We're going to break this up into three parts. Here in part A, we're going to talk about the idea of confounding, which is something that we mentioned back earlier in the semester. But we're going to talk a little bit here in this section about how can we identify confounding variables, and then a little bit about what we can do with them and how to take them into account. So let's start off with an observation. Often in a statistical study, we're looking for a relationship between an outcome and an exposure. So an outcome could be a certain type of disease, and then exposure could be some sort of risk factor for it. So examples, an outcome could be cardiovascular disease, and exposure could be systolic blood pressure, or specifically high systolic blood pressure. Another example, the outcome could be caffeine consumption, and the exposure is age. Maybe for some reason we suspect that age is related to caffeine consumption. Another example, obesity as an outcome and gender as an exposure. So maybe we think that gender is somehow related to levels of obesity. But these are all very complicated outcomes. Obesity, there's a lot of things involved with obesity. Gender is maybe just one of them. So there may be other factors involved. Likewise, cardiovascular disease, systolic blood pressure is related to that, but maybe other things like obesity is related to cardiovascular disease, maybe gender, maybe socioeconomic status, all sorts of different things may be involved. And so there may be other factors involved, and so in this chapter we're going to talk about some simple ways that we could maybe identify other variables and start to take them into account. So next, let's talk about a couple of definitions. The first one, confounding. That's a distortion of the effect of an exposure on an outcome by another variable. So we've got some exposure, we've got an outcome. That exposure affects the outcome, but maybe there's another variable involved. When there's another variable involved, or maybe more than one other variable involved, that's what we call confounding. Similar concept is effect modification, and this occurs when there is a different relationship between the exposure and the outcome depending on the level of another variable. So again, there's another variable involved, and maybe the level of that variable affects the outcome depending on that exposure. So as an example, the effect of systolic blood pressure on cardiovascular disease may be more acute in older patients. So we've got here an outcome, cardiovascular disease, we've got an exposure, systolic blood pressure, but there's another variable involved, age, and we may suspect that the level of age has an effect on the effect of systolic blood pressure. So that's an example of what we'd call effect modification. Now, another observation is that identifying confounders and accounting for them is very complicated. We're going to talk about just some very simple basic ideas and techniques for dealing with them. We could spend entire semesters talking about identifying confounders and how to deal with them. So this is a very complicated issue. So to try to illustrate some ideas involved with identifying confounders and accounting for them, let's look at example 9.1 from the textbook. And in this example, the question is there a relationship between obesity and incident cardiovascular disease? Now remember back from chapter 3 that word incident means kind of developing cardiovascular disease. So is there a relationship between obesity and the development of cardiovascular disease? A related word was prevalent, and prevalent just deals with having the disease at one moment in time, whereas incident means developing the disease over a period of time. And so they give some data here in table 9.1 titled Baseline Obesity and Incident Cardiovascular Disease over a 10-year follow-up. And so what they did here is they enrolled 1,000 people in this 10-year study. At the beginning of the study, they recorded whether each person was obese or not obese. So they had 300 obese and 700 not obese. And then over the 10-year period, they recorded the number of people who developed cardiovascular disease. So they had 106 develop cardiovascular disease, and then 894 did not. The numbers in the middle say, for instance, that 46 of the obese people developed cardiovascular disease, 640 of the non-obese did not develop cardiovascular disease, and so on and so forth. And so we're going to start to use this data to answer this question: is there a relationship between obesity and cardiovascular disease? So let's start off by calculating some numbers here, some summary statistics. Let's calculate the proportion of obese people who developed cardiovascular disease. And so we're going to take the total number of obese people, 300, as the denominator. The numerator is the number of those obese people who developed cardiovascular disease, which is 46. And so we get 0.153. So that means that in this study, 15.3% of the people with cardiovascular disease, or excuse me, 15.3% of the obese people developed cardiovascular disease. Now let's calculate the proportion of non-obese people who developed cardiovascular disease. So the denominator is the number of non-obese people. The numerator is the number of them who developed cardiovascular disease, 60. And so that comes out to be 0.086. So that tells us that 8.6 of the non-obese people in this study developed cardiovascular disease. Now notice that this proportion here is almost twice as much as that proportion there. So that's an indication that maybe obesity is related to cardiovascular disease, because about twice as many obese people develop cardiovascular disease than non-obese people. So to further illustrate that apparent relationship, we're going to calculate something that we called the relative risk, or also called the risk ratio. This is an idea back from chapter 3. So we're going to take the proportion of obese people who develop cardiovascular disease divided by the proportion of non-obese. We do that arithmetic and we get 1.78. So that relative risk, or also called the risk ratio, of 1.78 means that obese people are 1.78 times more likely to develop cardiovascular disease than non-obese people in this study. Now we have to add that qualifier, in this study, because we're not talking about the large population of all people. We're just talking about the 1,000 people in this study. And so based off of this, it again looks like the answer to our question is yes, there is a relationship between obesity and cardiovascular disease. But now let's ask another question. Obesity is not the only issue involved here with cardiovascular disease. We might ask another question: is age related to obesity? Maybe as people get older, they tend to get a little more obese, or maybe vice versa. So maybe age is a confounding factor here that we need to take into account. And so in table 9.2, titled Baseline Age and Baseline Obesity, we have the same group of 1,000 people. And this table categorizes people as either age less than 50 or 50 and greater. And then also records whether each was obese or not. So we had 600 people who were age less than 50, 400 that were age 50 plus, 300 were obese, 700 were not obese. This number says that 100 of the age 50 or less were obese. This number says that 200 of the age 50 or more were not obese, and so on and so forth. So let's just briefly look at these numbers here. Let's look at this row here. We see that half of our people age 50 plus were obese, whereas only 100 over 600, so 1/6 of our people age 50 or less were obese. And so that indicates that there's a apparent big difference in levels of obesity between these two age groups. So it appears that age is related to obesity. Based off of this data, it looks like as age increases, the prevalence of obesity also increases. Well, let's do a little bit of a formal hypothesis test to test this claim that age is related to obesity. And so we're going to go back to Chapter 8 and use our last type of hypothesis test, our chi-squared test of independence. Remember, our chi-squared test was used to test the claim of a relationship between two variables. And so in our test of independence, our hypotheses were that the null is that age and obesity are independent. Remember, independence is just a way of saying that there's no relationship. And then the alternative is that age and obesity are dependent. Dependent is just a way of saying that there is a relationship. So the null is that there is no relationship. The alternative is that there is a relationship. And so if we go to the Excel workbook chapter 9 and the worksheet test of independence, we have the same formulas here for doing our test of independence that we saw in chapter 8. And so remember what we do, we enter our observed data here, our observed frequencies, and this comes from table 9.2, and then Excel calculates these expected values, and then these contributions down here. Here's our test statistic. In this case it's almost 127, so that means there's a big difference between the observed and the expected. And here's our p-value, which is 0, or very close to 0. And so we come to our technical conclusion. The p-value is 0, which is much less than 0.05, and so we would reject the null hypothesis of no relationship. And so our conclusion here is that age is indeed related to obesity, or at least it appears that age is related to obesity. And so let's kind of make an observation now. So age is related to obesity, but obesity is related to cardiovascular disease. So in our original question, we were asking, is there a relationship between obesity and cardiovascular disease? And well, what this illustrates is that age is a confounding variable. Age affects obesity, and so the point here is that when assessing the relationship between obesity and cardiovascular disease, we must take into account age. We can't just ignore this variable of age because it appears to be a confounding variable. And so the next question is, well, just exactly how can we do that?